Okay. All right, I stopped because I'm going to go ahead now and introduce our speaker. So, Emil Petruncio. He is a former retired Navy captain, and he has served as an adjunct at our school since January of 2020. He had a 32-year naval career where he developed expertise in satellite remote sensing of the ocean, analysis of tides and internal waves, and the use of oceanic and atmospheric data and forecasts to support a variety of operations at sea and ashore. During his 12-year assignment as a permanent military professor at the Naval Academy, he taught courses in physical oceanography and military ethics to over 600 midshipmen, advised independent research projects, and served as a chair of the oceanography department. He also served as the director of the USNA's Center for Chesapeake Bay Observation and Modeling and co-director of the USNA's Sea Level Rise Advisory Council. Since 2013, he supported the Ocean Exploration Trust part-time as a navigator and expedition leader aboard EV Nautilus, conducting seafloor mapping and exploration of benthic habitats in the Caribbean Sea and Pacific Ocean. He's in fact given a talk about his deep sea exploration a couple of times for us. Dr. Petruncio has a Bachelor of Science in Oceanography from the Naval Academy, a Master of Science in Physical Oceanography and Meteorology from the Naval Postgraduate School, a Master of Science in National Security Strategy from the National Defense University, and a PhD in Physical Oceanography from the Naval Postgraduate School. So it is my pleasure to yield the floor to Emil, and you're all in for a treat.
Thank you, Anthony. Yeah, so I'll share a bit of what I've learned from serving on that Sea Level Rise Advisory Council at the Academy, and also a little bit of the ocean exploration off the California coast, where we looked at submerged ancient shorelines, and that kind of that calibrated my understanding of how rapidly sea level can change and how much it can go up over centuries. And so let me just start sharing here, and I'll try to ignore my black lab who's whining outside the door. All right. So, yeah, I'll just start you off here with a look at the city dock area of Annapolis, an area that is impacted by sea level now. You know, we can talk about whether you can attribute extreme weather events to climate change, but there's no doubt that the sea level change, the sea level rise that we've seen over the past century and that we're seeing now is tied to anthropogenic warming. It's pretty clear. And Annapolis is one of the many East Coast cities affected by this. So the city dock area floods quite frequently. And superimposed on here, I'm showing you some exponential growth curves. It's essentially some of the scenarios for future sea level rise that look like this, if you plot sea level versus time for the 21st century. So for those not familiar with the downtown, the city dock, I circled an area here in yellow. That's the monument, the Alex Haley statue, where he's talking to children about Roots, you know, the great novel he wrote about the slave, his ancestry and descent from the slaves brought to the U.S., and Annapolis played a part in that. But these statues have become icons for coastal flooding. They show up everywhere, and so I'm going to be referring to those in a couple slides here. So you see right next to the city dock area here, this big green roof here is the roof of the field house, the Halsey Field House at the Academy. So the Naval Academy campus is right next door to downtown, and we're working closely with the city of Annapolis on our future plans. So just so people understand the geography here, the Chesapeake Bay is oriented pretty much north-south. And so when you get southerly winds, not very strong, 12, 15, 18 knots, good sailing weather, those southerly winds, if they're sustained for, say, half a day, they're going to bring an extra foot of water up the bay and into the river here, affecting Annapolis. And that plus high tide gives us the nuisance flooding that we're seeing. Areas in green here, this is a topographic map, so areas in green are low-lying. They're vulnerable. I'll refer to this map later. It's from the Environmental Protection Agency. So here's the Academy. the lower, what we call the lower yard. This is the huge dormitory, one of the largest college dorms in the world, if not the largest. And we're surrounded by College Creek, Severn River, and Spa Creek. So we got water on 3 sides. And the Chesapeake Bay is filled to the brim. You know, it reached its present shoreline about 3,000 years ago. Sea level had been pretty steady since then until the past century. And now the Chesapeake Bay is overspilling its brim. It's pushing back. You know, we got a lot of landfill here, reclaimed land to build playing fields around the academy, and now the bay is trying to reclaim that land back. We're seeing frequent nuisance flooding, and here's what's the number of nuisance flood events per year from 1928 when we installed the tide gauge in Annapolis to present. And you see that from 1930 to 1970, we're typically getting 1 event per year, 41 events over 40 years. Then things started to increase after 1970, where we were averaging maybe 4 per year. And 2018 was a shocker. We had 41 events that year alone, and we've stayed there. We had 43 the following year, dropped back down to 30, but we're seeing this acceleration in the number of flooding events, and it's only getting, it's going to get worse. So here's what we're talking about when I say nuisance flooding. This is a low-lying road along College Creek, and high tide plus, you know, about a foot of water, we start to submerge this road and the road across the creek from it. On the right is what Hurricane Isabel did to us. It flooded the playing field that's shown on the map below it right here. That's Warden Field. That's a playing field. Warden Field is over here, but we've got several playing fields that flooded. About 2/3 to 3/4 of the campus flooded. Isabel caused $120 million of damage. That was a 5-foot water that came up the bay and stuck around for about a day before it subsided. So here's what we're looking at in the next few decades. This is monthly mean sea level for Annapolis in the lower left here, and a couple of curves, which are future scenarios that depending on the way emissions go. And the very likely range of sea level according to the Maryland Climate Commission. And the plausible range of sea level could be higher just in the next few decades. We're looking at maybe a couple extra feet, anywhere from a 1/2 foot to a 1.5 foot of sea level compared to today. And that will turn this nuisance flooding into a daily event, and Hurricane Isabel into like a 1 in 20 year event instead of, it was almost a 1 in 100 year event, not quite. But the daily flooding, the nuisance flooding is going to become a daily event, and the extreme water levels will become much more frequent without adaptation. So the National Climate Assessment is required every 4 years. That's an authoritative document that's vetted by all the government agencies, several federal agencies, and academia and the National Academy of Sciences. And the 2014 assessment said that just 2 more feet is going to triple the frequency of dangerous coastal flooding. So here we are looking at Alex Haley and his little audience, and this is the nuisance flooding, what it does to that area of the city dock, and this is what it looked like with Isabel. And all the storefronts, of course, were flooded. So $120 million of damage at the Academy and a lot more damage downtown. Are the dog barks coming through my audio?
Not noticeably.
I might. All right.
Just barely. It's not annoying.
If it becomes an issue, I will open up the door and let Coco in, and maybe that'll stop it. So just give me a high sign, Anthony. It's not just an event, a threat to cities, but ecosystems. This is the Blackwater National Wildlife Refuge. So I think it's 66 acres of wetlands and tidal areas that are going to be submerged. And whether you can create new wetlands inland depends on how much development has occurred inland. So if there are roads that bar the progress of the wetland further inland, then you're going to lose valuable ecological services here. Storing carbon, providing habitat for wildlife. And so Blackwater, like many other tidally flooded areas in estuaries, is certainly threatened. And that's down here, the lower right, this in Dorchester County on the eastern shore, where you see these purples and light blues indicate very low-lying or tidally flooded areas. Looking broader than the Chesapeake, river deltas are heavily populated areas around the world. They're fertile areas. You've got access to fishing, and Bangladesh, a country of 165 million, very threatened. That you frequently see, the impacts of cyclones that go ashore in the Indian Ocean there. But this map showing that by 2050, just with the current trends, you could have over 1 million displaced from this area. Whether they migrate to cities or try to move out of country remains to be seen. It's 90% Muslim population, and given the current events, Myanmar would not be a very willing neighbor to take in those climate refugees. They'd probably go to India or elsewhere. So it's a worldwide issue. The World Climate Research Program recognizes regional sea level change and the impacts as one of the most severe societal consequences of climate change and a grand challenge for research. And it is, the final pace and amount of sea level rise depends on greenhouse gas emissions. Spill the beans there, but I think everybody realizes now that the nations have come to realize that climate action is essential. So some of the research imperatives and what the World Climate Research Program is trying to coordinate, they're trying to focus on getting better estimates of paleo sea level. I'll show you some examples of estimates of sea level over the ages. Quantifying how much land ice is going to contribute to near future sea level rise. That's the largest contributor to sea level, but it's also the largest source of uncertainty in future sea level rise. Better observations of regional sea level change, and including ground subsidence, which is a regional factor that can affect how much sea level rise you see. Better prediction of regional sea level. I'll show you regional predictions appropriate for Annapolis, and there's a broad spread. So we need to try to reduce the uncertainty there so that managers of coastal zones have something more solid to work with. So I'm going to hit on several of those topics, those research imperatives in this talk. That was just my setup. I'm going to now move on to causes of sea level variation, then look at historical change, share a little bit about what we've observed off the coast of California that shows submerged shorelines. And then we'll look at what's happening today and projections for the future. So the changes, sea level changes are very short term and with very local effects, just due to waves, tidal changes, earthquake generated tsunamis, storm surge like Hurricane Isabel, the southerly winds creating the nuisance flooding, and oscillations, the decadal oscillations like El Nino, Southern Oscillation, there's the Atlantic Oscillation. These are local effects that make it necessary to have a regional model for your predictions. Things that affect global sea level, the major factors are the melting of ice from land, not sea ice, because that's already floating, it's raised sea level. But when you have a glacier calve and send an iceberg into the ocean, you've just introduced new water to the ocean, increasing its volume. The volume also will change due to thermal expansion as the atmosphere heats, and the ocean has absorbed 90% of the anthropogenic warming of the atmosphere. And then most of that 90% is in the upper levels of the ocean, causing expansion. So these are the major factors. There is also Some contribution, less than 25% currently, just changes in ground storage of water. Water that trickles down into aquifers and then is pumped out for human use. The building of dams in the 1970s actually slowed global sea level rise, but then things caught up and the sea level rise is accelerating again. Ocean dynamics is a regional factor. The Gulf Stream is a local effect that is contributing to sea level rise along the East Coast, the slowing down of the Gulf Stream. That's something that's got to be modeled locally. Isostatic adjustment, very long-term effect, goes on for thousands of years, but again, another regional effect. And so this, not only it highlights the importance of having a regional model, but it also is a factor that complicates going back millions of years and trying to estimate sea level, because you need better data on how isostatic adjustment is played out. All right, so this, and then plate tectonics can also affect sea level, and I will show you how. So here are the factors that affect global sea level: land-based, ice, melting, thermal expansion, and some minor contribution from land water storage. Again, the land-based ice melting is the largest source of uncertainty going into the future. It's about 2/3 from ice melt now and about 1/3 from thermal expansion, with a smaller contribution, again, from the land water storage. Here's how we know it's 2/3, 1/3. We've got, okay, in black here is sea level measured by satellite altimeters, radar altimeters on orbit, pinging off the ocean surface, measuring sea level very accurately. And this the satellite altimetry curve plots right on top of tide gauge data. It's very accurate. These other curves here are measurements of increased mass in the ocean from melting ice. That's been measured by the GRACE satellite mission and the GRACE follow-on mission that's up there now. And thermal expansion measured by these Argo drifters. We have over 3,000 of these drifters that go down to a preset depth, 1,000 meters, 2,000 meters, drift for 10 days, pop up, and transmit the temperature and salinity that they've measured while drifting freely with the currents. So we're getting very good measurement of the heat content in the upper 2,000 meters of the ocean or so. Good measurement of added, mass subtracted from glaciers and ice sheets added to the ocean. You add the red and blue curves together and you get the green curve, which matches up beautifully with radar satellite altimetry measurements. So we've got a very good idea now. Just in the past, I'd say 5 years or so, the papers have come out that have kind of closed the budget for sea level as we've been observing it. Here's the area of concern in terms of loss of land ice. In addition to Greenland, which is melting rapidly, there's a lot more ice that could come from Antarctica, and in particular, West Antarctica. All along here, we've got seabeds that are warming as ocean currents are cutting in there along the coast, undercutting these ice sheets. The Ron ice shelf and Ross ice shelf are large ice shelves that are not as affected because they're pinned in place by some large islands. But along West Antarctica here, the ice shelves are retreating, which is allowing glaciers to advance towards the ocean. So here's a particular area of West Antarctica, the Thwaites Glacier area and Pine Island Glacier. This area of the Amundsen Sea in West Antarctica could add 4 feet to global sea level, just this area alone. The Pine Island Glacier has retreated at about a rate of 1 mile per year over the past 2 decades, and the Thwaites Glacier is retreating at about half that. But these the ice shelf off of the Thwaites Glacier. So these ice shelves have been described by I think it's Michael Alley at Penn State as the flying buttresses of the European cathedrals. These ice shelves hold the glaciers back. If you remove the ice shelf, the glacier can now accelerate towards the ocean and add more water to it. Take away those flying buttresses, the walls of the cathedral collapse. So this area is being scrutinized by researchers. We want to answer some, fill in some knowledge gaps. We don't have a good understanding of how glaciers calve and form icebergs. You know, at what point is that ice shelf weak enough to crack and send these glaciers free, or these icebergs free? The interaction of the ice sheets with the warm waters and the interaction of the ice sheets with the ground, with the bedrock. These are areas that we need to improve in order to fine-tune our scenarios for the future. So that's those are the contributions to global sea level. Contributors to regional sea level include, well, the fingerprints of those ice melt effects. So the ice melting from Greenland and Antarctica will not be distributed evenly around the globe. Due to gravity and Earth's rotation, there will be bulges of water that move away from those areas and impact other parts of the world. We will feel an impact from Antarctic ice melt more than the continent of Antarctica will. It'll actually move away from that continent and affect other areas. We're now to the point where NASA has some impressive models that are showing these regional fingerprints. In addition, you have dynamic sea level, say the Gulf Stream, or warm blobs of water like the eastward slosh of warm water associated with El Nino. That's dynamic sea level. And then vertical land movement. The big one here is glacial isostatic adjustment. As the glaciers retreat, the land around from the Ohio Valley out to the mid-Atlantic, from the Great Lakes out to the mid-Atlantic is rebounding and is sinking. The land further north, where the glaciers were most recently covering around Canada and Alaska, is rebounding. So relative sea level is actually falling in parts of Alaska and Canada, but relative sea level rise is accelerating around the mid-Atlantic because of subsidence associated with glacial isostatic adjustment. There's also an impact from removing groundwater. Not a big factor around Annapolis, but the lower part of Chesapeake Bay around Norfolk, where there was a lot of groundwater extraction, that has exacerbated the situation. Again, these need to be considered in regional models. Okay, so that's a look at what causes the sea level. And here's what we're seeing in Annapolis. So globally, there was about 6 to 7 inches of sea level rise over the past century. What we saw in Annapolis, since the tide gauge was installed about 90 years ago, is 14 inches. Half of that's due to the land subsidence that I just mentioned, half due to the absolute sea level rise. So here's a little diagram of this glacial isostatic adjustment. Back at the last glacial maximum, 18 to 20,000 years ago, the ice sheets were covering North America, and the mid-Atlantic area here where we were in the forebulge. So if you push your hand along the bedspread, you're going to bunch up the sheet in front of your hands, and that is the forebulge here, with the ice sheet being the hands pushing that land up. Since then, the glaciers retreated. The forebulge has been sinking at a rate of about almost 7.5 inches a century. And that's expected to stay at that rate for thousands of years to come. It's a very slow process. So while this land subsidence due to glacial isostatic adjustment has comprised about half of our sea level rise signal over the past century here in Maryland, it's going to be the land ice melt that begins to dominate here in the rest of the century and for centuries to come. Okay, those are causes. Let's look at historical sea level rise. This is a lot of information here. The geological time scale and the eras, periods, and epochs. And what I want to point out here is that for the 4.6 billion years that Earth has been around, 85% of that time is greenhouse conditions. That's what's normal on Earth. Ice-free conditions on Earth. No ice on either pole. Warm, much warmer climate conditions. And then we've had 5 including the present, ice house conditions or ice ages. Ice age is a term that can be a little confusing. Some geologists, paleoclimatologists apply it to the ice house conditions, which can last several million, tens of millions of years. Some folks use ice age to refer to glaciation periods that occur within ice house conditions. So I'll try to avoid that confusion. We've had 5 ice house or ice ages, and including the present, the late Cenozoic ice age is what we're in now. That onset was about 34 million years ago with the formation of an ice sheet over Antarctica, and then the Quaternary glaciation of this ice age, 2.6 million years ago, was marked by the formation of the Arctic ice cap in addition to Antarctica. So that's the present condition we're in. We're in a glaciation stage, a glaciation, but we're in an interglacial period. The glaciers have retreated, but we're still in an ice age. The transitions between greenhouse and icehouse are most likely caused by changes in the greenhouse gases, atmospheric CO2 and methane, and or the closing of, cutting off of ocean currents, warm ocean currents that when you cut them off, you allow an area to cool, and that's what's caused our current Quaternary glaciation. And I'll try to show you that. Here are some passages. The Drake Passage between South America and Antarctica, and Tasmanian Gateway between the southern tip of Australia here, Tasmania, and Antarctica. Those opened up roughly, 35 to 40 million years ago, and that's the onset. That marked the onset of the late Cenozoic ice age that we're in. That allowed currents to circle Antarctica and isolate it from the warmer currents closer to the equator. And so you had an opportunity for Antarctica to start cooling off. And then later on, the Isthmus of Panama closed off, and the Indonesian Seaway, although it's not totally closed, became much more restricted as Australia northward towards Asia. And so that marked the onset of our Quaternary glaciation that we're in within this late Cenozoic ice age. So these ocean gateways, ocean circulation is really important for controlling climate. Here's a look at the surface currents in red, the deep currents in blue, and so you see this Antarctic circumpolar current that could start flowing once these ocean gateways were opened up. And we see a surface flow here driven by the easterly trade winds that used to flow through the Panama area, but when that Isthmus of Panama was closed off, now we could start sending more moisture up into the North Atlantic and cause snowfall and higher albedo, cooling temperatures, and the Quaternary glaciation. The flow, there's less warm water flowing through the Indonesian passage here that is also affecting the amount of moisture going up north in the Pacific. So the ocean gateways, in addition to the greenhouse gases, are important in transitioning us between greenhouse and icehouse conditions. So now let's look at the past million years, which we can get from oxygen isotopes in seafloor sediments. The general trend here for the past 5 million years is a gradual cooling from and sea level dropping by about, well, from 5 to 3.5 million years ago. This area in light blue here, sea level dropped about 15 meters, 45, 50 feet or so. 3.5 to 1 million years ago, there's a steeper drop in sea level, about 60 meters, almost 200 feet. But we start to see these large scale fluctuations that have a period of about 41,000 years. If you do some Fourier analysis of that signal. And then in the past million years, sea level was still mostly lower than it is today, but you got these large fluctuations, rapid excursions of about 100 meters. And the frequency of those, the periodicity of those is now about 100,000 years. and sea level is mostly below today's level, with the exception of the previous interglacial periods, the Eemian, which was the most recent interglacial before the current one, and then this Holsteinian one about 400,000 years ago. So this periodicity, what's driving that? And that is where our orbital variation comes into play. These Milankovitch cycles that are affected by the eccentricity of the Earth's orbit, the obliquity of it, the tilt of the axial tilt of Earth's orbital axis, and the precession, the wobble of that tilt. These have different frequencies, about 100,000, 41,000, 21,000 years. These factors come into play. This is affecting the amount of incoming solar radiation, the intensity of it. These come into play once you've got an ice age in place. So looking at past million years or so, here are the contributions from the variation in the solar insolation from the Milankovitch cycles. Here's the sum of those at 65 degrees north. The net effect of these Milankovitch cycles is to cause this yellow line, this variability in the solar radiation at 65 north in the summer. And that is well correlated with the changes in the stages of glaciation that we see. Now there's a little bit of a lag. You get an increase in solar forcing leads to a slight temperature increase, but then that temperature increase is amplified by the greenhouse gases. So you get like a dial that's turned by the solar forcing, but then the greenhouse gases really flip that dial and cause a rapid increase in temperature. And then, so there's about 100, most of that 100,000 year period is 80% of that is the glaciation, the glacial period. And then there's a short interglacial period caused by that warming, amplified by the greenhouse gases. So the Milankovitch cycles are affecting the solar radiation part of this diagram of the greenhouse effect. But it's these greenhouse gases that amplify it. And it's also major changes in the greenhouse gases and ocean circulation that will transition you out of an ice age and into a greenhouse, or vice versa. Just to put things into perspective for these long-term changes in climate. So over the past 800,000 years, this carbon dioxide has been well correlated. You know, you get the temperature increase, then a carbon dioxide increase. Basically, I mean, there's a lot of things that affect the carbon dioxide levels, but one major example is as the ocean warms, it can absorb less CO2. It can hold less CO2 in solution. And so you're putting more into the atmosphere. As the ocean cools, it can absorb more CO2. And so that cooling trend will also be show up in the CO2 levels. But boom, we have upset the equilibrium that has existed in these glacial and interglacial periods. We are now, it was just a very recent article, the highest CO2 level in something like 3.6 million years. Certainly higher than any of these glaciation stages of the current ice age that we're in. So before we look at what's going to be the impact of that CO2 in the future, let's look to the past to see how sea level has changed since the last glacial maximum. Just a quick clip here from the Ocean Exploration Trust on exploration along the California borderland. Oops, I think I need to rewind this. Yep.
What we do know is that sea level was much lower than it is right now. 22,000 years ago, it was about 120 meters down. And then as the great ice sheets all over the world began to melt, level began to rise. In geologic terms, we call it the Holocene transgression. Robert Ballard, and I wear a lot of hats. The one on my head right now is president of the Ocean Exploration Trust, but I'm also sitting in the Inner Space Center at the Graduate School of Oceanography, where where I'm the director of the Center for Ocean Exploration. And what we're doing is we're searching for the caves of what's called the last glacial maximum. This is the lowest sea level got 22,000 years ago. It went up suddenly, laid there for a couple thousand years, went up again, went up again. During that rise, it didn't just rise continuously, it stopped 6 times, and those are called still stands. So think of it like a staircase. During those still stands, the sea attacked the cliffs of the shoreline, and we believe made cave systems, and then were flooded, and did it again and again. So what we set out to do was first find those ancient shorelines, which we did in 2016. Then in 2017, we started going along those ancient shorelines, looking for cave complexes. And we found them at the top 4 levels. In the shallowest levels, we then sent divers in. And in some of the cave systems are quite complex. And this year, we're going to the deepest level, looking for caves. We mapped them last year, and now we'll be hunting for the caves at 100 meters and 110 meters.
So here is, it's a pretty interesting exploration going on there off the California borderland. I was on a couple of those ROV expeditions, where we put ROVs in the water. Divers explored some of the shallow caves that are down to, about 8 meters deep near Santa Cruz Island. But we used the ROVs to explore caves at these depths where we expected to find them based on some research of sea level change in the North Yellow Sea. This is a global phenomenon where since the last glacial maximum here, 21,000 years ago, so we've got time on the x-axis here, 21,000 years ago on the right side, to 6,000 years ago on the left side. And sea level, relative sea level, going from 0 today down to 120 meters. So sea level began to rise at about 19,000 years ago. There were a couple short surges and then a big meltwater pulse here, MWP 1A, meltwater pulse 1A, about 15,000 years ago, where sea level rose like 30 meters over a few thousand years. Very rapid rise. And there have been a few other meltwater pulses. So in between these rapid rises, we had still stands, and that's when these caves were carved. And it's really remarkable that we were able to find caves at several of these depths predicted by the graph of still stands over the past, since the last glacial maximum. And actually, near one of these caves, there was a freshwater spring. We could see water coming up out of the seafloor. And near that spring, we happened to come across what we're very confident is a woolly mammoth tusk. Woolly mammoths were roaming Southern California at the time. We just couldn't date it because most of the organic material was replaced by rock. It's become petrified. So they couldn't do carbon dating on it. But the expert at the Harvard Museum of Comparative Zoology said, yeah, I think you got a woolly mammoth tusk there. They have found bones of them on the Channel Islands. So that really put into perspective for me what can happen in the future. These predictions that I'll be showing you of sea level rise as large as, say, 12 feet over this century ahead of us seemed enormous to me, outlandishly large. But then when you look back and see how sea level has surged since the last glacial maximum, it's not out of the realm of plausibility. We've got good measurements from tide gauges here in blue, and then the era of satellite radar altimetry began in the 90s with TOPEX, and then JASON 1, 2, and 3, and now Sentinel-6, which was launched in November, providing us very accurate measurements, and you see an acceleration of the rate of sea level rise. And this typical tide gauge that we have now in Annapolis, it's the acoustic tide gauge, pinging sound off of the oceans, the water level surface, and then transmitting that data by satellite to NOAA. But very good agreement, and as I showed you previously, there is multiple lines of evidence that supported what we're seeing with radar altimetry, besides the tide gauges. And here's a zoom in on just the satellite altimetry era, and there is an acceleration going on. And it's the fastest rise in the past almost 3,000 years. This is not a big shocker. You know, Al Gore didn't invent climate science. This Swedish scientist, Svante Arrhenius, back in 1896 said, hey, humans can impact climate by putting CO2 into the atmosphere. And that's what we're seeing. The temperature anomaly here graphed with the CO2 concentrations. There's little doubt at all now that the warming that we're seeing is anthropogenic sources. And by modeling it, you can only reproduce the temperature changes we see. This is temperature going back to 1900 to 2000. You can only reproduce that by including the human factor, the greenhouse gases that we've emitted. Natural factors alone, the volcanoes, solar cycles, are not able to reproduce that warming. So we are in a climate now that is comparable to other warm stages in the past where sea level was much higher. So if we look back 125,000 years to that last interglacial, the Eemian interglacial period, temperatures were roughly what we're seeing today. CO2 was not as high, and sea level was 6 to 9 meters higher. Now this could play out over several centuries, but it's very plausible that that's where we're headed with our sea level rise. Going back further to 3 million years, carbon dioxide is about what we have today, and due to those regional adjustments, uncertainties about glacial isostatic adjustment, et cetera, there's a large uncertainty into what sea level was back then, but anywhere from 10 to 30 meters higher. So this is, you know, prior to the Quaternary glaciation, there was no ice cap up north, but there was some ice in Antarctica. But without ice in Greenland, that's what you're looking at, 10 to 30 meters. So for future scenarios, we use two approaches. We can look to the past, which is what I've just been talking about, and the semi-empirical method just uses statistics. Temperature was this, carbon dioxide was this, and sea level was this. So we come up with relationships there to try to predict into the future. But you know, some of those processes contributing to sea level change in the past may be different from what we see in the future. You know, we're certainly creating an unnaturally high amount of carbon dioxide in the atmosphere. So those statistical relationships might not hold. The other alternative is to physically, you know, get these equations into a numerical model that you run on a supercomputer and try to predict sea level rise. But there's we still have a ways to go to understand how glaciers will respond to this warming. So we use both approaches, and NOAA came up with these scenarios. For the extreme scenario here for 2100, 2.5 meters relative to the year 2000. That's more from the semi-empirical approach, what we've seen from input of rapid ice melt in the past. And some of these, and that would be, you know, that would be associated with greenhouse gas emission scenario that's unconstrained, that we keep pumping into the atmosphere more and more CO2. But it's plausible, but we don't know enough to actually put a probability on that scenario. And then they just kind of evenly space them out, going down to the lowest scenario would be continuing a linear trend of what we're seeing today. But the train has already left the station for that linear trend. So to help guide our efforts at the Academy in deciding which scenario to adopt for our planning purposes, we turned to the National Climate Assessment Part one was the Climate Science Special Report that came out in 2017. Part two, the impacts around the US came out in 2018. But they said, looking at all of those scenarios, they consider these to be the most likely for anywhere from 1 to 4 feet by 2100. And I just put the intermediate scenario, Noah's intermediate scenario on there to show you how that compares to the very likely scenarios. Now, when they say very likely, they're pretty confident out to 2050, but that upper level, they have lower confidence in as you go out because it could be much higher. But this is their best guess as to the likely range. So we've adapted the intermediate scenario, partly because of that guidance from the National Climate Assessment, and also because that's the way our sea level has been tracking. Here's monthly mean sea level. I just updated this the past week to include the months of January and February 2020 in here. And this monthly sea level rise is tracking right along with the intermediate curve. That intermediate curve also intersects with what the Maryland Climate Commission said we could expect for a growing emissions scenario. If we can stabilize emissions and make major carbon cuts, stabilize it by 2050, and also scrub CO2 out of the atmosphere, maybe we can stay down in this green area and mitigate the sea level rise. But regardless, sea level is going to keep rising out into the next century. And if if we go with business as usual and keep pumping CO2 into the atmosphere, it'll continue for several centuries into the future. There's already a thought that we've probably delayed the next glaciation period of this ice age that we're in, and that will stay in an interglacial for at least 50,000 years. That's some recent research. So with that intermediate scenario, we're looking at 4 to 5 feet along most of the mid-Atlantic relative to 2000 by 2100. Higher sea level change in the Gulf Coast there due to the subsidence around the Mississippi, mouth of the Mississippi. And then we've got sea level rise as an issue with these Pacific Islands, many of which are U.S. territory, looking at 3 to 4 or 4 to 5 feet of sea level rise. They don't have a lot of land to play with there. So there's already, Fiji has already purchased some land in another Pacific Island nation to move their people to when it becomes time. In addition to the sea level rise, you also have to plan for the more frequent storm surge, which I mentioned at the very beginning of the talk. Hurricane Isabel will become like a 1 in 5 year storm by 2100 with this intermediate scenario. So when you're talking about what to protect against, you got to take that into account. It's going to add to your costs, but we don't want an Isabel-like flooding every 5 years. Prevention is always cheaper than repair. So here's a quick look at the city dock area again as it stands today, and large parking lot, a lot of parking here, but this whole area is slated to go away and be replaced by an elevated park. What you don't see here is a seawall that would join up with the Naval Academy seawall. They're looking at a variety of options, but this is from the City Dock Action Committee's final report. Cost about $60 million and timed for 2024. The seawall, they're looking at maybe temporary ones that could either rise up from the ground or be put in place, glass panels or transparent panels, not glass. But they are also one of their working groups said, yeah, if you're going to build something that's going to be around for 75 years, you better plan for this intermediate scenario, which is about 4.3, 4.4 feet of sea level rise in Annapolis by 2100, plus storm surge. So this elevated area, I think, is about 8 feet above sea level. Less parking, more pedestrian, and you'd also let the water flood some areas. The Dutch and Germans have learned to let the water in and live with water, and that's going to be essential, I think, an essential part of the adaptation measures. So, and this is where it would tie in with the Naval Academy's seawall over here by what they call Gate Zero. So Annapolis is an area that can afford to adapt. There's going to be some areas, many parts of the world that can't afford to adapt, and so that's going to be an issue. But to sum up, we've just disrupted the normal cycle of atmospheric CO2 levels, and that's driving atmospheric temperature increases, which in turn is driving the land ice melt, the largest contributor to sea level rise at present, and it's going to become an increasingly larger part of the puzzle in the future. So Annapolis can adapt, but millions of people are going to be unable to adapt, especially from deltas and other low-lying areas, the Pacific Islands, et cetera. Climate change is a research focus by the international research community. They're trying to improve paleo sea level estimates, get a better handle on how the glaciers will respond, glaciers and ice sheets. Human behavior, though, is a separate issue. That's up to the governments to try to rein in the greenhouse gas emissions. But the planners can't, you can't just be paralyzed by the uncertainty. You've got to consider how much risk you're willing to take with a given project, and how much you want to spend on protecting it against what level. And so you choose a scenario, take the extreme water level events into account, and start planning. But the adaptation planning has to start now. So there's some references here, some sea level rise viewers, and I could look into making the brief available on some share drive to the club. I'll leave you with some art. I was staring at these submerged shorelines off of Southern California long enough, so this is like a imaginary bathymetry here and some exponential growth curves from staring at these future scenarios so much, and I call this one exponential, expo-notional. I haven't exhibited this one yet, maybe in the future. Something similar like this was exhibited online though. All right, thanks. I will stop sharing here. And I guess we have about a minute or so for questions.
If anybody has any questions, feel free.
Yeah, I see a lot in chat.
Yeah, the chat looked like it was mainly premature mentioning of all the club information. I was going to do that at the very, very end, and I hit send by accident. But there's a whole bunch of information, folks, on that if you're interested. But more importantly right now, well, firstly, Emil is fantastic, and I think just thank yous and round of applause for him for another sensational talk. Leading into his next one, which will be art and science, I think. It's only just, yeah. Yeah, if anyone has any questions now, for a couple minutes, we can take a time for one or two questions. Just to also note, who just, Elise is the one who just asked about questions. Elise is currently the president of our Super Duper Club. So I just wanted to just let you all know that she's done some wonderful work and has been very active and helpful for the last couple of years, actually. And then there's that too. Anyway, so does anyone have any questions for Emil?
I saw a question from Mary there. How long did you say the next glaciation is delayed by? There was just some recent research that I saw that said 50,000 years. So, these typically, the interglacial periods last 10 to 15,000. We've been at it, the glaciers started to retreat 18,000 years ago. So we'd be coming up on a glaciation period within a few thousand years normally, but that looks like that has been delayed. And yeah, 50,000 is what I saw. I could see if I could try to find that reference.
Okay, great. Thank you.
Oh, I have a question.
Yep.
I know they had talked about doing things to attempt to stem. I know we're already committed to a certain amount of the rise, but they were talking about like seeding the ocean with iron to help with production, which absorbs, I guess, more CO2, and also doing that deep or dumping a bunch of CO2 deep into the ocean where it's colder and where it can hold it more. Are we getting more serious about trying to do those things, or are they still just something we're throwing around and hope,
There is talk of geoengineering. I'm not sure how practical it is, but there is a lot of talk on ways to decrease the amount of incoming solar radiation or absorb CO2 either in the oceans or scrub it from the atmosphere, turn it to rock. They've demonstrated that in Iceland, pumping it into the ground and turning it into rock. The question is, is there still time to geoengineer? How much can we avoid? Because there could be some tipping points we've already crossed with methane release from the permafrost. There could be some things set in motion there that we might not be able to reverse. So we're committed to, I'd say at least 6 feet of sea level rise, if not more, in the next couple centuries, probably more. But yeah, geoengineering is a whole nother subject there, another brief, but and there's also a lot of work into how to adapt our cities, floating cities, while we're trying to slow things down.
It's a scary thought to think of how we're committed to something. Nothing we can do. It's like car with no brakes.
The ocean's got a slow response. Yep. And there's feedback loops. Yeah. Lots of feedback loops that we're still learning to model.
Oh, yeah. Thank you, Professor Petruncio. This is Dan. If Professor Shear doesn't mind, I thought I'd make a plug for you because you'll also be making, I understand, another presentation during the Maryland STEM conference coming up. Is it going to be on sea level rise and ocean exploration? And that conference will be held in May 1st. So
May 1st, thanks. Yeah, the ocean exploration talks are approved. Still waiting to hear about sea level rise. There might be a separate one on that. While I take the Navy.
Question.
Yeah.
So actually, I got 2 questions. Did you say that in the past we have sea level rise that's more severe than now? And then my second question is that you said the during the greenhouse time, I think we said was like 85% of the time of Earth is around is in the greenhouse time. Did you say that
Yes.
during the greenhouse time the poles does not have ice?
Yes, Amy, 85% of Earth's history has been greenhouse conditions with no ice, no land ice, too warm for it. And that is when sea level was hundreds of feet higher. The 2 more recent periods that I talked about were during this current ice age that we're in. The last interglacial period, 125,000 years ago, sea level was about 6 to 9 meters higher. And if we go back 3 million, a little over 3 million years, there was perhaps with some ice in Antarctica, but no ice in Greenland, sea level was 10 to 30 meters higher. And trying to narrow that estimate down is an area of research.
Oh, okay. Thank you.
Sure. So yeah, James Hansen of NASA has been doing a lot of this paleo climate research, and he's been criticized for having a rather shrill warnings about how much sea level could happen this century. But he's not wrong about the long term, based on what we know from paleo sea level, that yeah, large increases could be expected to play out over centuries. Nice turnout for a Friday afternoon. Thanks for coming out, folks.
Gotcha. Okay.
So, all right.